Greetings and welcome to another video on aviation safety risk management through hazard analysis. This video is going to take on a topic that is quite a bit more complex and technical than some of the previous videos. This video is going to look at situations where there's very low risk and the idea of a risk ceiling and how to develop that. One of the things before I start that I'd like to point out is that in today's world, there's a saying that there's an app for everything, and that's also true for risk management. Everything that I'm about to show you can be automated. So if the math or the statistics seems a little bit overwhelming, try to see through that and focus on the concept itself, because just like a calculator, if you understand what the calculator is doing, you no longer have to have those skills like long division or any of the other things that you would use a calculator for. So in our previous videos, we took some data that we had with regard to a traffic intersection, and we organized that data in a risk framework and performed some initial risk calculations to get a sense of what the risk looked like. But what would we have done if the data was different? And what we're interested in here is what would happen if over the 10-year period we looked at and the 1.1 billion vehicles that went through this intersection, what if there were no accidents? Well, what we cannot say about this is that the probability of an accident in the future is zero. All we can say is that we haven't seen an accident over the last 10 years. And so the follow-on question becomes, with that information, what can we say about risk? That's really the topic of this presentation. And to get to the answer to that question, we need to understand a little bit about probability theory and how it applies here. So we're going to develop a risk ceiling. And what this is a case where we have no observed accidents, and we want to understand what the maximum accident probability could be. In other words, how high could the probability of an accident be and still allow us to believe that we could go 10 years without seeing an accident? So let's take a look at this. We're going to start off by looking at the binomial distribution. Now, there are a number of different distributions that are available to us in probability theory, and if the assumptions that I'm going to lay out here don't apply, then the underlying concept is still valid, but we would almost certainly have to change to a different distribution. It really just changes the math that's going on under the hood. So here are the assumptions that would sort of invoke the binomial distribution. And the first one is we need some number of independent trials. Now, what I want to point out here, because this is really the important part of this assumption, is in the previous slide, you saw a piece of data that said there were 1.1 billion vehicles that passed through an intersection over 10 years. We want to focus on the first part of that, the number of vehicles, because those could be considered independent trials. Each vehicle that went through was exposed to the risk. But the 10-year thing is specifically something we would have to change distributions if we wanted to focus on that. And the reason is, over the next 10 years, we don't know how many vehicles will go through that intersection. So what we're going to do is we're going to choose the 1.1 billion vehicles, and we'll say this is what we've seen over the last 10 years. And now moving forward, our risk horizon is going to be the next 1.1 billion vehicles that passed through the intersection, regardless of how long that takes. There also has to be a way of describing success and failure, and in this case, we would say that a success is getting through the intersection safely, or a failure being an accident. Although you could reverse those labels, and sometimes it's a little easier to do that just mathematically. And last, we have to have some probability of success, whatever we define success to be, and that has to be the same for each one. In other words, all of the cars need to be exposed to the same probability of an accident. So if those assumptions are true, and we can apply those in the real world, then we can use this distribution. And here's a quick example of how it works. A coin flip is probably the easiest example to understand. we flip the coin, it can either come up heads or tails. So we call one of those success and we call the other one failures. Let's assume heads is success. And now let's think about flipping this coin 100 times. And if we believe the probability of heads is 50%, it's a fair coin, we can calculate what we would call an expected value. This tool is an incredibly powerful tool in probability theory, especially for communicating things like risk. And it's really simple in this case. All we do is we multiply that probability times the exposure, or the number of trials, and 0.5 times 100 gives us 50. So this is our expected value. But the term expected value can lead you down a wrong path. In other words, if you flip a coin 100 times, do you expect 50 heads? Not exactly. In other words, you wouldn't be shocked if you saw 51 heads in that experiment. You wouldn't be shocked if you saw 49 or 48 or 52. Those would all be very reasonable outcomes that you would expect to see. So what does that look like in a graphic form? Here's what a binomial distribution looks like specifically for the coin flip. And you can see that sure enough, right over 50, we have the highest blue bar, indicating that is not only the average, it's the center point of this symmetric curve or distribution, but it's also the highest probability outcome. But you can see on either side of that, in descending order, things get less and less likely. In other words, if you were to flip the coin 100 times, you could certainly believe that 60 heads might show up, or 40. Those are well within the boundaries of this distribution. But you can see how the blue bars start to taper off as we get up around 67, 68. It would be very unlikely to see 70 heads out of 100 throws. Is it possible? Absolutely. Is it likely? Not at all. But when we start talking about flipping a coin 100 times, the chances of it coming up 100 heads out of 100 tosses, it's just not believable. The probability is so low, it's effectively zero. It couldn't happen in our lifetime. So what we would do if we observed 100 coin tosses and 100 out of 100 were heads, we would question the probability. We'd say it can't possibly be a 50% probability of heads. And that's the logic that we're going to apply moving forward. So let's increase the level of difficulty a little bit here to give us an example where we can apply this approach. And it's the idea of throwing 5 six-sided die. I've labeled this a Yahtzee example if you ever played that game growing up, or if you come from a naval aviation background like I do, you might be more familiar with this sitting at a bar somewhere playing a dice game. In any event, what we're interested in is the probability of rolling these 5 dice together and having the outcome be all ones, or 5 aces. Off the top of anyone's head, it's hard to determine what that probability might be. Now, we know that the probability of this event is not 0, but it's a fairly small probability. And we also know that if we put our minds to it, we could calculate this probability analytically. But in a lot of the situations where we would apply this technique, that's not possible, or it's just so cumbersome that we wouldn't be interested in taking the time to try to calculate it. So here's what we do. Let's suppose that we throw these 5 dice 5,000 times, and during that entire time we don't have a single instance where it comes up 5 aces. What can we now say about the probability of 5 aces? Well, our intuition tells us it's got to be a pretty small number, but how small? This is what we're going to attack, and we're going to start by stating a hypothesis, and we just want to kind of get ourselves into the ballpark. And a really good technique for this is to start off by saying, I'm going to create this initial hypothesis of 1 in whatever my trials were. So in this case, 1 in 5,000. That'll be my starting point. So if I now assume that that is the probability of rolling 5 aces for just a moment, I can now use the binomial distribution to determine how likely it is that over 5,000 rolls, I would see 0 observations, or 1, or 2, or 3, and so forth. And this is what it looks like. So what we have here is a graph that shows the probability of seeing 0 outcomes over 5,000 dice rolls is somewhere in the neighborhood of about 37%. And it turns out that it's equally likely that we would see one of them. And you can see as we start to ask the question, what about seeing this happen twice in 5,000 rolls or 3 times? You can see the probability gets smaller and smaller. And once we get to 5 or more, again, the probability is just so incredibly small that we would not expect to really ever see that outcome. All right, so with that in mind, the way that we need to look at this particular graphic is to focus on that 0 bar. Because one way of reading this information is that there's about a 37% chance of not seeing 5 aces, but that means there's about a 60-something% chance of seeing it. In other words, it's more likely than not that we would have seen at least one outcome of 5 aces if we tried rolling the dice 5,000 times. And so what we want to do now is we want to sort of leverage that idea to get to a point where it's a little bit more believable that we would actually see 0 observations. So if we remove those dice and start moving into the next part of this, let's set a target of 50%, a 50-50 chance of seeing this particular outcome. Rolled the dice 5,000 times. There was a 50% chance that I did see a 5 ace outcome, and there's a 50% chance that I didn't. This works a lot like another concept in statistics where you essentially assign a confidence level. So 95% confidence, for example, and that will dictate how wide your margin of error is. This works essentially the same way, although it's not exactly the same concept, but the idea is along the same lines. So as analysts, we can choose this target for ourselves, and experience has shown that 50% is a really good technique and it works in most situations. But from time to time, we may want to increase it or decrease it, and you'll see in a moment what that's going to do to our probability estimates. So for now, we'll just stick with the 50% target. And here's what this looks like. So what I've done is I started with 1 in 5,000 as a probability of 5 aces, and I iteratively increased it to 1 in 6,000, 1 in 7,000, 1 in 8,000, and then I found out that I had gone a little too far, so I just kind of walked back and forth until I arrived at 1 in 7,250. And that's almost exactly a 50% chance, or it results in a 50% chance of seeing 0 5 ace outcomes in 5,000 throws. Another way of saying this might be easier to think about is if I threw the dice 5,000 times and called that an experiment, and then I repeated that experiment and I did it over and over again, roughly half the time I would expect to see no outcomes of 5 aces in those experiments. So with that, what does that look like? What does 1 in 7,250 look like? Well, we just do the simple division, and it turns out to be, sure enough, a pretty small number. But what's the actual number? What if we now take the time to calculate the exact probability of rolling 5 aces on one throw of the dice? You can see the probability, the actual probability, is a little bit smaller, but our ballpark estimate was pretty darn close. It's certainly a usable estimate. And also notice that our hypothesized probability is higher than the actual probability. And in a risk management application, this is a valuable technique because in most cases this means our estimate is going to be more conservative than the actual probability, the underlying probability. Now, what happens though if I didn't have 5,000 rolls available to me? What if instead I only had 1,000 rolls to look at? So 1,000 rolls and 0 observation. Well, what I would do is I would go right back to square one and I would start with my new hypothesis, 1 in 1,000, and then I would iteratively change it until I got to a point where I had a 50% chance of 0 outcomes. And what that leads me to is a place where my new hypothesized probability is still in the ballpark, but you can see it's about 7 times higher than what it was before when I had a larger sample size. And this relationship is very important, and it's consistent anytime we use this. The longer we go and the more trials or operations that we conduct without seeing the outcome of interest, like an accident, the more we can say about the probability of that accident. In other words, the lower we can assume the probability is. So let's go back to our traffic example. So now what we have is the exact same framework that we had previously, and let's just assume that nothing has changed with regard to the hazard probability or the distribution of outcomes. We really want to focus on that center term, the probability of an accident. And we've observed 0 accidents, so now what can we say about the probability of an accident? We can't say it's 0. Instead, we're going to apply the technique we just used. So in the upper right corner, I'm going to just put some notes. And the one thing that I know for sure, because I get to choose this as an analyst, is I want to look out at the risk horizon, and I want to look at the next 1.1 billion vehicles that are going to go through this intersection. And the logic here is just that I looked backwards in time at the last 1.1 billion vehicles, so that's how far I've chosen to look into the future. Now, I also need to set that target that I talked about, and the 50% target seems to work out really well, so I'm just going to continue to use that. In other words, I want a 50-50 chance of seeing 0 accidents over this number of vehicles going through this intersection. So what happens? Here's another binomial distribution. It looks remarkably similar to the ones we just looked at for the dice throw. And what I've done is I've just iteratively changed the probability until I got to a point where I had a 50% chance of 0 accidents. What does that number look like? Well, it's a really small number expressed here in exponential notation because it's so small. So with that, what I can do now is I can remove this graphic and I can just perform the calculations again. Just multiply those probabilities together to get my new likelihood values, those joint probabilities. And here's what it looks like in a risk matrix. And if you saw this risk matrix in the previous videos, you saw that the risk was much higher when we had accidents in our data. Now that we don't, what we're showing or what we're intending to communicate in this risk matrix is that those blue circles with the black dots in them that are labeled the current risk, what we're saying is this is the highest risk that we can believe might exist and still give us 0 accidents over 10 years. The black line that drops out of each one, making it sort of look like a pin, is trying to communicate graphically that the probability could be much lower. It could be 1 in 10 billion, 1 in 100 billion, 1 in a trillion. We have no idea how low the probability could be, but we've established a ceiling here. There's no way we could believe that the risk could be much higher than what's displayed here. That's all I have for you in this presentation. I hope it's helpful to you, and look forward to seeing you in the next video.